Section 2.1, we're going to start looking in this chapter at functions. And in particular, in this section, we're going to start out with what a definition of a function is. I know you've heard about functions before. This is not a new concept, but we may be doing some different things with it that you haven't done or haven't done recently as well. So let's take a look first. The definition of a function is a rule that assigns each element in one set to a unique element in a second set. So, taking a look at and thinking about these sets, the input is what the first set would be. So like the first set that's sort of described in that definition, this is our first set. The output would be the second set. And if we're thinking along those lines, we can also refer to the first set as the independent variable. So again, this is the first set. And then the dependent variable is the second set. All right, so you guys know I don't do multiple choice questions on tests or anything like that. The point of all of the different language on the screen is that if a question asked you to identify the input or to identify the independent variable, you should know what they're asking you to find. And they're asking you to find the first set of information, the first grouping of data. There's other names, a couple more names that we will find and that we will see associated with these. The first set is often called X when we're dealing with like an ordered pair, X's and Y's. And then the second set is the Y's. A couple other names that you've seen these done or used is domain and range. Domain being the X values, the input, the independent variable, range being the Y values, the output, or the dependent variable. So we're going to use these sort of interchangeably to mean the different parts of this function relationship. All right, I'm going to do an example first. It's a very contextual example, real life kind of stuff that kind of shows all of the different things that you have to consider when you're deciding if something really is a function. Okay, so I'll let you write this one down first. So suppose C is the cost of mailing a letter, or you could equivalently say package or something like that if you wanted, but letter will work just fine. W is the letter's weight. And then we're going to answer the question, is C a function of W? Is W a function of C? Are they both functions or are neither one functions? This kind of feels like multiple choice, but we will deal with each of the pieces separately and then be able to answer the question. All right, so one of the inherent problems with word problems or context problems is that some of you have a lot more real life experience with this particular context than others might. Right? So if you asked this same question to me or you asked it to my 19-year-old son, our experiences are going to play on what we know about the context of this problem, right? I mail things. I go to the mail probably twice a week for various whatever's going on. It just happens. My kid, I don't know that he's ever been to the post office. It's just not a part of his everyday life. So his context and his ability to answer this question is going to be tainted by that experience. Do you guys know what I mean? I remember having a student it's been a long time ago, college algebra class, who is from Russia. And word problems were just a booger for her, not because her English wasn't good. Her English was fantastic. But the context just didn't make sense always because the context was from an American standpoint, not from a Russian standpoint. And so she had a sort of a disadvantage because of that. So some of what we're going to talk about just is going to be about this specific context of this problem. So you're going to imagine that you're going to the post office, okay? There's two variables at play in this problem. There's C and there's W. What is C? the cost, probably in dollars, right? And W is the weight, and because it's a letter, it's probably weight in ounces. These items don't really matter, but just to be aware of them. Okay, there's a unit that we're using here. And the first question asks us, is C a function of W? So that phrasing of W tells you that W is the input in this particular part of the question, and C would be the output. And then the next part of this question flips them, okay? So is C a function of W would mean, can this work? Can I make the weight the input, and that wasn't spelled right, let's try again, the input, the cost to the output, and call this a function? I mean, I can make them the input and the output, but are they a function if I do that? So let's imagine going to the post office, and we have our letter, right? And our letter has a specific weight. And we give our letter to the person behind the desk, and we ask them to mail it, all right? If this is a function, it means that there's one and only one price that I could pay to mail that letter. That's what it would mean, literally. I give them the letter, they tell me the price, I give them money, we're done. Okay? If this is not a function, it would mean that I give them the letter, it's got one weight, and I have choices. I have options. I have different amounts of money I could pay to mail that same letter. So what do you think? Do I have choices, or is there only one and only one choice when I mail that letter off? Okay, what might I have choices surrounding? Like why might I have choices, Lena?
Well, what if you expedite it? So you send it at a faster rate, and then it's pay more money to get it there in 2 days instead of getting it there in 1 day.
Okay, so there might actually be another variable in this equation. I mean, not literally, but in this situation, right? There's something else that's varying how fast I send it. Does that make sense? So this would not be a function because I have choices. I have more than one option on how I could actually, or what I could actually pay to mail that letter. So this is not a function because there's not one and only one amount that I could spend to mail this letter. Does that make sense to everyone? All right, let's switch it around. All right, so now I have the output. I'm going to try and switch it with my input. Because the other question says, could W be a function of C? In other words, if C, the cost, were held fixed, would I know for sure the weight of the letter? So now put yourself in the position of the person behind the desk. All day long, you're telling people amounts of money of their cost of their letters to mail. If you know that that letter costs 50 cents to mail, do you know for sure the exact weight of that letter? Or are there options? What do you think, April?
I think you know for sure.
Would you? Okay. So if I haven't handed her the letter yet, but I know it's going to cost one stamp, which is one stamp 50 cents? I was having trouble remembering this before my other class. 40 something still? Okay. 47? All right. We'll go with 47. Sounds good to me. 47 cents. So I'm the clerk behind the counter. I've got a 47-cent cost to mail this letter. And the question is, do I know for sure the letter weighs 0.5 ounces? Or could it weigh 0.51 ounces? Do you see my question, April? It could, right? So when you are mailing postage, the reality is that there is a range of weights that all cost the same amount for that one stamp, for example. My example was the one stamp, right? And the reality is, if I were to go and I put in the mailbox, a bill, and I put in the mailbox a check inside there, or I put the check and the receipt that I'm supposed to mail back inside there, it's still going to cost me one stamp. But those rates are going to be slightly different. Not a lot different. They can't vary a lot and give me the same price, but they can vary. Does that make sense? One price actually covers several different weights, infinitely many, because it's on a spectrum, right? A continuum. It goes from 0 ounces all the way up to, I think it's 1 ounce. I think 1 ounce is the cutoff for one stamp. All right, so again, the answer would be no, it's not a function. And the reason, again, is because there's a variety of weights, like a spectrum of weights, that all correspond to the same postage amount. And there's a threshold, right? At some point, you've exceeded the amount of letter, the amount of piece of paper you can actually put in that letter, and it will bump you up to the next price. But again, then you're at another spectrum of weights that all cost that new price to mail at that new rate. So this doesn't work. So the answer is actually on this one that neither of these are functions. All right, so why do I bring this up? I don't necessarily bring this up to try to make the issue confusing, but I kind of do. I bring it up because I want you to see that there's more going on behind the scenes of this simple question than it meets the eye at first, right? It's really easy to just say yeses or nos without an answer that makes a lot of contextual sense. There's a lot of context in one simple little problem. All right, so we're going to sort of back off the context now and look at things from a numerical perspective next, okay, in terms of functions. And we're going to take an example of what happens when we look at a graph. Now, show of hands, I promise I'm not going to ask you to actually tell me exactly what you remember, but who remembers having learned about the vertical line test? All right, most of you do. That's what we're looking at next, is the vertical line test. Very specifically, one sort of description of the vertical line test would be that this is a graph, that a graph will represent a function if and only if no vertical line is able to intersect the graph in more than one point. And I absolutely hate defining something by what it doesn't do, and that's exactly what this definition says. It will be a function if it doesn't have these characteristics. Super crazy stuff. We do it a lot, though. Right? We do it a lot, even with our English and in other contexts. So I'm going to give you 3 graphs, and I want you to write down yes or no. That's all I want you to write down, and then we'll go through them, make sure you have the yes or the no written correctly, and that you know why it really is yeses or nos. So these 3 graphs, what you're trying to decide is, do they represent a function? So here's my first graph. And you don't need to be too very specific on where things are crossing axes or anything like that. Just a sketch is fine. B should look like a circle, even if it doesn't really quite. Pretend for me. There's my third one. The shape is kind of what we're going for here as you're sketching them, just the shape. So write those in, draw those down, or draw those on your paper and write down yes or no. Is it or is it not a function? Okay? And it's all based on this vertical line test that's talked about here. If I draw vertical lines, will they or will they not cross graphs more than once? What do you think about A? Is it a function? It is a function. The answer is yes. I'll draw my picture in just a second. Is B a function? It is not. It's a no. And is C a function? And it's a no. So let's go back now and talk about why on each of them. Okay, so what we're doing is we're drawing, or even if you don't actually physically draw them, you're mentally drawing vertical lines. And vertical line is, by definition, straight up and down. It's a terrible sort of description, but it is, right? Vertical means straight up and down, no slanting to it. And I can't draw infinitely many of them, but the image has to work no matter where I draw a vertical line. Every time I draw a vertical line on the first graph, it will cross the graph exactly once, right? That is what it means to be a function from the vertical line test. That when I draw my vertical lines, they don't cross the graph more than once. Now, on the second graph, if I try to do this, I either draw a line out here, and it crosses the graph not at all. And if I did that, that's totally okay. I can have lines drawn that don't cross the graph. That does not have anything to do with whether it's a function. But there are places, in fact, again, there are infinitely many places on this particular one, that when I draw the line, the vertical line, it crosses the graph twice. We could even say, I'll give approximations. Let's say that this is 2, 3, and 2, -3. So what happens is this vertical line fixes the x value, right? Everywhere along that vertical line that I just drew, it's a fixed value. And I said, let's just say it's 2 for the sake of argument, right? Everywhere x is 2. The problem is that because it crosses the graph twice, there are 2 y values that are associated with that x value, 3 and -3. And that's exactly what it means to not, whoops, sorry about that, not be a function. A function needs to be a rule that assigns each element in one set, those are the x's, to a unique element in the second set. And my graph assigned it to 2 elements, 2 y values. So it's not a function. Okay? So that's what we see happening on part B. And of course, C does the same thing, right? There are places where I can draw vertical lines on C that cross the graph twice. And if it crosses the graph twice, it's assigning one x value to 2 y values. Would it have to be exactly twice? What if I had a graph, I'm not going to draw it in fully, but if I had a graph that did this? Would that fail? Yeah. I'd cross the graph lots and lots of times, potentially, right? So a specific x value would be assigned to many y values. Again, not a function. All right, so we're going to sort of back off of the idea of functions for a moment. All of these graphs are graphs, and they do represent what's called relations, okay? So we're going to look at what a relation is. A relation is simply a set of ordered pairs, or a collection of points. You could define it that way, a collection of points. They don't have the same restrictions that a function does. It doesn't say one input makes one output. It doesn't have that extra layer of description on it. It's very broad. It's just a collection of points. You could have a whole collection of them all over your graph. Maybe you've done math classes where you've had what are called scatter plots, done something with statistics or whatever. It's just a bunch of collection of data. Okay, that's what a relation is. Now what we're going to do on numbers 3 and 4 are to determine whether this collection of data, this relation, does determine a function. Okay, it is 3 and 4. They are both relations. Okay, what we don't know yet is, are they functions? And there's a couple of ways that you could look at whether these actually fit the description of functions. One way is obviously we could plot them on an XY ordered pair, and we could draw vertical lines. Okay, so we could do that. Agreed? It would look a lot like it did in the last slide. I want to show you another way of doing it when you've just got a small collection of data that works really nicely too. So another way of doing that is we're going to make 2 circles. They're really going to look more like ovals. The first one's going to look, it's going to be yellow, and the second one's going to be white. And we're going to let our x values be in the yellow circle and our y values be in the white circle. And if we repeat a y value or an x value, we don't list it multiple times. It's already listed once, we move on, okay? So the first ordered pair is the ordered pair 1, 7. 1 is the x value, 7 is the y value. The second point is 0, 7. So 0 is the x value, 7 is the y value, but I've already listed 7 in the y circle. The third one is 4, 6. 4 is the x value, 6 is the y value. And the fourth one is 9, 6. So 9 is the x value and 6 is the y value. I've already listed 6, so I won't list it again. Okay, so I'm just separating the pieces, putting all the x's in one circle, putting all the y's in the other circle. And then what we're going to do is we're just going to draw arrows connecting them. Okay? So if it's connected as an order, if it's an ordered pair, we're going to connect it with an arrow. So the first ordered pair was 1, 7, so I'm going to draw an arrow from 1 to 7. The second ordered pair was 0, 7, so I'm going to draw an arrow from the 0 to the 7. The third one is 4, 6, so I'm going to draw an arrow from 4 to 6. And then the fourth one is 9, 6, so I'm going to draw an arrow from 9 to 6. Okay, so let me just say again one more time right now. If you don't like the way that I'm showing this and you like the idea of doing the ordered pairs better, that's fine. I'm just trying to give you another option of how to think about it, okay? So if you like this one, fantastic. If you don't like this one, go to ordered pairs in a graph. That'll work. All right, so what the question is, if this is a function, is does every x value correspond to exactly one y value? In other words, if I pick an x value, so somebody pick one of the x values I've got. 4. X value of 4. Does the x value of 4 go to only one y value? Yes, it does. What does the x value of 4 go to as a y value? 6. It only has one output. Now, I know that the outputs double up, but that's not the question about functions. The function question is, do the inputs only go to one output? And the answer for this is yes, they do. This is a function. And the reason is because each x value corresponds to only one y value. That's the y. So let's look at the second set. Part numbers, what would it have? Number 4. I'm going to draw my circles the same way. We're going to collect our data in an x circle and in a y circle. And we're going to draw our arrows. So my x ordered pairs, let's see, it's 7, 1. So 7 in the x circle, 1 in the y circle. The next one is 7, 0. So 7 in the x circle, I already have that. 0 in the y circle. The next one is 6, 4, so 6 in the x circle and 4 in the y circle. And then the point 6, 9, so 6 in the x circle, which I already have, and then 9 in the y circle. So I'm hoping you noticed that all I did was switch the circles, right? I just swapped the x's and the y's, okay? All right, we're going to draw our arrows the same way. 7 as an x value corresponds to 1 as a y value. 7 as an x value corresponds to 0 as a y value. That's the second ordered pair. 6 as an x value corresponds to 4 as a y value. For my third ordered pair. My fourth ordered pair is the 6 corresponding to the 9. The question's the same. If you pick an x value, does it correspond to one and only one y value? It doesn't. In fact, they correspond to 2. All of them do in this particular scenario, right? If you picked the x value of 6, it has a y value of 4 and a y value of 9. And that fails to be a function. So this one is not a function. And so it's no, because, and it doesn't have to be each x value, but there's at least one x value. We have more than one, but there's at least one x value. That corresponds to more than one y value. So it fails. It's not a function. These are still both relations, but only the first one is a function relationship. Okay, so going back, yes, ma'am.
Okay, so, like, you can't have, like, 2 of the same x's going towards a different y.
Correct. And if you think about it from drawing a graph, like if you were to draw this picture, we would have an ordered pair at 7, 1, and we'd have an ordered pair at 7, 0. They'd be 2 dots directly above one another on a number, like on an XY ordered plane. If you drew a vertical line, it would cross both dots. So that would fail from a vertical line test sort of a picture from that perspective too. Mm-hmm. Yeah, lots of ways to look at it. Yes, ma'am.
So, you
You have to be careful. Looking for repeat x values is not necessarily going to help you, but if the x value repeats, the y value that corresponds with it would have to. Like, for example, up here, let's say we had 7, 1, and we had another 7, 1. That'd be okay. Because, yeah, the x value repeats, but it repeats with the same y value. So you have to be careful of looking for just x repeats, because if the x and the y repeated together as an ordered pair, that'd be okay. So, yeah. All right, thinking about our functions, whether they're functions or relations, actually, we can talk about domain and range. We mentioned it on our very first slide, and we're going to do 3 examples of that now. We're going to go back to ones that we've already done for the first couple. So the first one says we're going to look at number 2a. That was a graph. It was this graph where I've drawn in all my lines now. Let me take the lines out. All right, here's my graph on part A. And what we're going to do is we're going to identify the domain and the range. All right, so we're going to think about this one from a graphing standpoint. That's why I selected it. So if you were given a graph and you're asked to find the domain, then what you're going to be doing is you're going to be looking for what x values am I allowed to have on this graph. In particular, we usually look at a graph from left to right when we're talking about the x values. So if I start on the far left-hand side of this graph, how far left can I go before I don't have any more graph, x values of a graph to be looking at? Negative infinity, right? Like I can continue going left forever on this graph, agreed? I mean, it's not going to go left very fast because it's going down really steep, but it's still going left. So the domain on this one actually would start, the x values would start at negative infinity. So my domain, that's a D for domain, would start at negative infinity. And as I'm moving from the left to the right, how far right can I go? Infinity, right? Because it continues moving along the graph. There are x values forever. Another way you can think about it is if you were walking along the x-axis and you were looking up and down, right? You just go up and down like this along the x-axis. Are there any places where you don't have x values? Is there a place where the x values stop occurring or where they start occurring? And on this graph, no matter where you are on the x-axis, you look up or you look down, you've got some x values there, right? Everywhere you do. So this domain is from negative infinity to infinity. Now the range is much the same way, except that instead of looking up and down at the x values, you would be walking, sort of climbing along the ladder of the y-axis and looking left and right for y values, okay? Or you can think about starting as far down as you possibly can on the y-axis, looking left and right. What is the smallest y value you ever see? Negative infinity, because again, this arrow indicates that the y values go down forever, right? So my range, my y values here, include all the way down to negative infinity on the y-axis. And if I'm climbing up the ladder, looking left and right, are there any y values that I don't see? Well, no. Now, if I get to a certain point, I look left and right, maybe I see multiple y values, right? That's okay, that's no problem. But I see y values at every point along the y-axis, to the left or to the right, there's a y value. And where do the y values stop? Infinity, right? They don't stop, in other words, really, right? I keep climbing up and up and up, and I can never get high enough that there aren't y values present. So this goes to infinity. So from a graphing standpoint, we can think about the graph moving left and right, up and down, and I'll do another one where we consider that in a second. The second example was number 3, the ordered pairs, okay? So on number 3, when we're looking at domain and range, it is a function, by the way, right? But even if it weren't, we could talk about the domain and the range. On this one, the domain and the range are simply a collection of data points. I only have 4 points in the whole relationship, right? The whole function is just 4 ordered pairs. So if I were looking at the domain of this particular one, what are the domain values that I have?
1, 0, 4.
Yeah, I just have 4 points, right? 4 numbers. I can write them in order, I don't have to, but if I write them sort of in numerical order, I'd be doing 0, 1, was it 4 and 9? 4 and 9. So my domain on this one is not an interval, negative infinity to infinity. It's just 4x values, because that's all I have. I only have 4x values. What would my range be?
7, 6.
Yeah, just the 2x values, 6 and 7 or 7 and 6. The order's really not important, but it's just those two values, that's it. Now on the third example here, number 7, I'm given an equation. There's a couple of things. We could graph them in a grapher, and some of you have graphing calculators, and that's fine if you do that. I'll look at that perspective in just a second. But you can also do this one pretty straightforward from the equation itself. This is a square root. All right, we're talking about graphs. This is the real number system, no imaginaries, okay? None of that's happening right now because we're working in the real number system. So tell me what you know about radicals in the real number system, square roots in particular. Who's talking? I hear you. What, is it Molly? Okay, what about the negatives? There's a positive and negative. Well, there's not on this one because it doesn't say plus or minus in front of it. If we put a square root on, there's a plus or minus, which I'm glad you brought up. That will come about when we talk about range. But what about the radical part itself? What's allowed to be underneath it? Positives. I don't have square roots of negative numbers in the real number system, right? In order to do square roots of negative numbers, I have to use imaginaries. And that's not the real number system, that's the complex number system. So right now our focus is simply real numbers, which means no square roots of negatives. In particular, what that means is that the piece that's underneath the radical has some restrictions. That 5 minus x has to be greater than or equal to 0. Right? Not just greater. It's okay if it equals 0. What's the square root of 0? 0. Yeah, that's totally fine. It's not very exciting, but it's fine. All right? So this would be my restriction on my x values. X values are a domain, right? So what I'm working with right now is figuring out the domain. I haven't graded this part of your test, but presumably you know how to solve this inequality, correct? Yes, you do. I know you do. So you've subtracted the negative, or subtracted the 5. So that the negative x is greater than or equal to negative 5, then what? Divide by negative 1. What do you have to remember when you divide by a negative? Yeah, you switch the sign. So, oops, I said it and then I didn't do it. So it was greater than or equal to, now it's less than or equal to, and negative 5 divided by negative 1 would be 5. So you can either write the domain from this one as an inequality, x is less than or equal to 5, which is fine. Or if you wanted to write it as an interval, it would be negative infinity to 5 with a bracket. Either of those notations would work. Now, let's come back to what Molly said about the plus or the minus. We don't have a plus or a minus on the front of this, right? There's not one. If there were one, my answer here would be slightly different. But there's not one on this one. So because there's no plus or minus at the beginning, what is this understood to be when you take a square root? Positive. Somebody said it, Julia. Yeah, it's positive, right? So the square root of 25 would be 5, and the square root of 72 would be, I don't know, but it would be positive, right? Okay, so yes, we're going to deal with positive values. So my range from this, the values that come out of this, are y values that are positive, or they could be 0 because the square root of 0 is 0. So this is greater than or equal to 0, or if you want to do an interval, that would be 0 to infinity. So you can do this from an equation standpoint, all right? You could also grab your calculator and you could graph it, and if you did, that would be okay. If you graph this on your calculator, this is a rough estimate of what you're going to see. It'll look like that, okay? And it will actually hit the x-axis right here at 5, 0. That's an ordered pair 5, 0. So if you're thinking about this from a graphing standpoint, like we did the earlier one from problem number 2a, if you were looking at the x values and you started on the left-hand side. All right then. Any questions about domain and range? Because we're about to shift gears. This is our last shifting of gears. Okay? All right, our last shifting of gears is going to talk about function notation. Up until this point in this lesson and prior to now, we've always talked about x's and y's. X is your input, y is your output, x is your domain, y is your range, all that good stuff. Well, this is function notation. This g of x, it means the same thing as y. And I know some of you are saying, well, then why didn't they just say y? For the same reason that you call me Dr. Hands and my husband calls me Krista. Right? I have more than one name. Functions do too. That's the deal. They have more than one name. This notation is actually really nice to be used for certain things. In particular, this says y equals x squared. I mean, that's what it means. But the notation right here is very friendly because what this notation says, without actually having to say it, is replace the x for y and simplify it. That's a lot of words. G parenthesis 2 close parenthesis. Way faster. Right? It is. It's really nice notation. Shorthand. That's what it is. It's shorthand notation. All right, so first of all, not first of all, but in addition, those parentheses don't mean multiplication. Parentheses are like the worst mathematical convention ever because they mean so many different things. It's all about the context. The parentheses mean multiplication. The parentheses mean ordered pairs. The parentheses mean intervals. And now the parentheses mean a name of a function, or at least part of it. And you just have to interpret the context you're in to know what it means. This context means it's part of the name of the function. And we read this as g of x. So the parentheses read as the word of. All right, so the example number 8, line 2, says g of 2. And what it means is replace the x with 2. So everywhere I previously have an x, I replace it with 2. And I always put it in parentheses so that if I do have negatives involved or whatever, or if there's multiplication, I don't forget those pieces. So what is 2 squared? Well, it's 4. The next one says g of negative 2. Again, it means replace the x with negative 2. And this is a really good example where the parentheses matter. If I put the negative 2 inside the parentheses, it means negative 2 times negative 2. If the negative's not inside the parentheses, the negative's not repeated. I mean, that's what it really means. So what is negative 2 quantity squared? It's also 4. Now, number 9 is a little bit different. It's a different name. Okay, fine. It says f instead of g. That's not really important, okay? But what you do notice is that the function itself does not just have x squared. It has 3x squared minus x. It has more going on. But it means the same thing. When I'm looking at f of 2, it means replace the x with 2. I just have more x's to replace. So instead of an x squared, I'll have a 2 squared. Instead of having minus x, I'll have minus 2. I've got to replace all of the x's with the 2. And then we simplify. Order of operations and everything still apply. Exponents start first. So what's 2 squared? 4 times the 3 is 12. So that first piece is 12 minus the 2 that's in the second piece, giving me a grand total of 10. Now notationally, the second piece, or the last piece on the screen, f of w, is like the simplest thing ever to do. Because it means replace the x with w. And not only that, it means that because it's just another letter as opposed to a number, I can't simplify anything. That's great. So I replace the x with w. I have 3w squared minus w. Okay? So function notation is just shorthand telling you replace the x with, and then it tells you what it's with. And here's why we're using it and why we're talking about it. Last piece of information in this section is called the difference quotient. You may or may not have seen this. Like legitimately, you may never have encountered what I'm about to show you on this particular screen. Some of you probably have. This is the difference quotient. F of x plus h minus f of x all over h. for some given function f. Jot it down. Some of you are nodding. You have seen it before. I promise I'm not going to put you on the spot and tell you to come do it on the iPad, okay? Some of you have seen it before. If you've taken like a college algebra, like an algebra 3 kind of class in high school, or math analysis, calculus, they all occur in there. This will show up in all of those classes. All right, I'm going to show it to you a little bit differently, though. I was not sure if I wanted to do it this way, and I decided this morning that I did, and I think it worked pretty well in my first class, so we're going to see how it goes in here. I'm going to show you a 3-step method. Step number 1 is that we're going to find f of x plus h. Okay, we're going to do it, and then we'll do step 2. Step 1, finding f of x plus h. All right, so we take the function that we were given. It's the last, similar to the last one that we did in the previous screen, 3x squared minus x plus 7. And what this says is I'm going to replace the x with x plus h. So that's what I'm going to do. Everywhere I previously had an x will now have x plus h. So I previously had 3x squared, so now I have 3x plus h squared. And I previously had minus x, so now I'll have minus x plus h. And then the plus 7 stays. It doesn't change. Okay, replace the x with x plus h. Write that phrase down if you need to. Replace the x with x plus h. And then we're going to simplify that. So the first one, don't forget, but the first one actually is foiling, so it's x plus h times x plus h. And if you multiply that out, you get x squared plus 2xh plus h squared. Write it out if you need to see it. And then I'm going to distribute the negatives, so I have minus x minus h and plus 7. The last step to clean this up would be to distribute the 3. 3x squared plus 6xh plus 3h squared minus x minus h plus 7. And you are done with step 1. Replace the x plus h and simplify. That's step 1. Step 2. Is to subtract f of x. All right, so we take the thing we just found, 3x squared plus 6xh plus 3h squared minus x minus h plus 7, and I subtract f of x. So I put a minus and then a parenthesis, and f of x they gave me. I don't have to find it, I don't have to come up with it. It's part of what I was given in the problem. It was 3x squared minus x plus 7, right? So I'm just writing it down. It's just one additional step in the process. And here's the cool thing. If you did part 1 right, it means that everything I just wrote down in the minus the parentheses is going to show up in the thing that I did from part 1 and get to be canceled out. All of it will, right? This 3x squared is minus 3x squared, and there's a 3x squared over here. So this piece and this piece cancel. The minus x right here is subtracting, right? It's removing the x, negative x, and there's a negative x right here. So those cancel. The positive 7 right here has a positive 7 right here, and so those cancel. So the process, everything in the problem became easier, right? There's less going on now. I have fewer items remaining. In fact, what do I have? Let's see. I have 6xh plus 3h squared and minus h. That's all I have left. Again, if you did it right at this point, every term, there's 3 of them, has an h in it. Do they? They do. So step 3 is to divide by h. Okay? And when I say divide by h, I mean each piece will be divided by h. I'm going to write it that way because it'll be easier to avoid one of the errors if we write it that way. So I've got 6xh divided by h plus 3h squared divided by h minus h divided by h. So what is 6xh divided by h? 6x. The h's cancel, right? So this is 6x. What is 3h squared divided by h? 3h. One of the h's on top cancels with the h on bottom, leaving me with 3h. And then what's h divided by h? 1. And it's negative because there's a negative still in the problem. And then we're done. All right, we'll do one more example like this, all those same 3 steps, and I'll just label them 1, 2, 3 so that you know which step we're on. Our example is that g of x is equal to x squared minus x plus 3. So our step 1 is to find g of x plus h. So we'll replace the x plus h, or the x, excuse me, with the x plus h in our equation. So this is x plus h quantity squared minus x plus h, and then plus 3. Of course, we have to FOIL out that first x plus h, which is x squared plus 2xh plus h squared, and then minus x minus h plus 3. And unlike the last one, that's actually as simple as it can go. There's no further simplified steps. So step 2 would be to subtract the g of x equation. So we've got the same x squared plus 2x h plus h squared minus x minus h plus 3, and then we're going to subtract the g of x equation, which was x squared minus x plus 3. And provided we've made no mistakes, we have all of these in that set of parentheses that will cancel out with something previous, which will simplify our expression down. So we are left with 2xh plus h squared minus h. And then step 3 is to divide each piece by h, and everything will have an h in it. So this will simplify, again, if we've done the process correctly. Oops, that's a minus. H over h. Okay, so 2xh over h, the h's cancel, leaving me with 2x. H squared over h, one of the h's on top cancels with the one on bottom, leaving me with plus h. And then h divided by h is 1. And we're done.